There are a lot of definitions and theorems in this section. I want to make one video to kind of wrap everything together, tie everything up, summarize everything. So here's my summary chart for all different properties, 5 things I've written on here. Let's take a look at each one of these in turn. So the first thing here in the top left is f is the gradient of little f. This is the definition of little f being a potential function for big F. And big F is the gradient. Big F is a gradient field here. F being conservative says that the integral along any path from A to B is the same for your vector field f. It does not depend on the path you take. It only depends on the vector field f and the starting and ending points. And so we have these two definitions here. Down here, integral of f dot dr is equal to little f of b minus little f of a. This is like a statement, an abbreviated statement of the fundamental theorem of line integrals. And so theorem 1 here is saying if your vector field can be written as a gradient field of some potential function, you go down here. Maybe I probably shouldn't write this as if and only if. Theorem 1 is going in this direction, although going in the other direction we'll get to in just a second. But theorem 1 is really going in that direction right there. Okay, then we have theorem 2. Conservative fields are gradient fields. Conservative fields are gradient fields. These two being the same thing is theorem 2. Theorem 3, the loop property, the following are equivalent here. Integral of f dot dr is equal to 0 around every loop C and D, and f is conservative. This is the loop property to show that these two things are the same. And once you have this, once you have the loop property, you can go from here to here. We do get if and only if. And then finally, we have the component test for conservative vector fields, which says that your vector field f is conservative if and only if you satisfy these cross-partial derivative conditions down here. The appropriate cross-partial derivatives are equal to each other. So this is the component test. But we have to be careful here in the case that, our region is simply connected. And so in the last video in this section, we'll see what happens if we don't have a simply connected region. But so assuming that we are dealing with a simply connected region, all of these properties are interchangeable. And so this makes our life really nice. If you have a vector field, found in an open simply connected domain, and you can tell it satisfies the component test, it's conservative, which means you have path independence. You know that you can evaluate it. You can evaluate line integrals that are path independent just by plugging into the potential function, and that the potential function must exist, and you can go ahead and crunch it out. And if I happen to ask you about some loop question, well, then you just know that you can get 0 here. So everything on this sheet, these are all interchangeable. So that makes your life really, really, really easy, because you can move back and forth between any of these. If I tell you that f is the gradient of some little f, you have the loop property, stuff like that. Okay, so I guess just be aware that I can ask you different parts here and realize, I tell you that I have a vector field f that has the property that the integral around any closed loop C gives you 0 of it, well, you know f must have a potential function. You know f must satisfy the component test. Everything here is interchangeable. Okay, to wrap this up, here let's just have you practice find potential function. So find a potential function for f is 2xy z inverse, z plus x squared z inverse, y minus x squared y z to the negative second power.